Next, we're going to continue talking about inferences for the difference of two population means. But this time now, how the samples are taken is different from what we had previously when we had the samples taken independently from one another. Now we have what are called dependent samples. So how the sample was taken from population 1 is going to depend upon how the sample is taken from population number 2 and vice versa. In the end, this actually will be very beneficial to us to be working with dependent samples. What I mean by that is that, let's say if we're doing a hypothesis test for the difference of two population means, we will be more likely to find that difference in a dependent sample situation than an independent sample situation. So let's next talk about, well, where would these dependent samples occur and what do they actually involve? So an example, let me get my red pen out here. An example that I have often had my students actually go out and perform the experiment itself is to determine, well, which grocery store has lower prices on average? Let's say if we want to compare Walmart to Hy-Vee. And the key to doing this kind of experiment is to sample the same items at each store. In other words, have, let's say, match the two items up or pair the two items. So for example, maybe let's say you go to Walmart and you get a box of Wheaties, and let's say maybe it's, I don't know, $4. And then you go to Hy-Vee and you get the exact same type of item. And again, it's Wheaties. And it is, let's say, $3.95. So $4 at Walmart for Wheaties. $3.95 at Hy-Vee for Wheaties. So now how we've sampled this item, Wheaties in terms of an actual breakfast cereal, how we've come about and sampled this item is dependent of one another at the two different places. Perhaps, for example, a particular brand of milk, whatever that brand might be. You sample that same brand at Hy-Vee, you sample the same brand at Walmart. So now again, the samples are connected in a way, they're dependent. Another example where dependent sample comes about, dependent samples come about, is, let's say you have some kind of medicine you're taking, maybe it's allergy relief medicine. And you're interested in, well, does an allergy relief medicine actually work? Does it provide relief on average to patients? And so a pharmaceutical company would be very interested in something like this. When they do a clinical trial, they would investigate this. And the way that they do it is that for, let's say, the same person, before they take the drug, and then maybe a couple hours after they take the drug, they take some kind of measurements on that same person to determine if there is relief or not. And they do that with one person, they do this also with a second person, and so on, so that every single person is contributing essentially two responses from, let's say, a population, before the drug is administered and after the drug is administered. Another example is that, let's say we're interested in this with respect to advertising. Has overall sales at McDonald's stores improved on average with their new advertising campaign? So before the campaign started, we have some measurement of sales for a particular item. After the campaign has gone for maybe a month, you look at that for that same item at that same store, how have sales changed? What are the sales now? And lastly, which of two types of running shoes has the least wear after 1 month? You know, maybe you get a pair of Nike shoes and also a pair of some other pair of shoes. And let's say a person wears brand 1, let's say on the left foot, brand 2 on the right foot. And after, let's say, running for a month or a month period of time of wearing them and having periodic runs in them, you measure how the tread has degraded over time. Since the same person is being used for the two different types of shoes, the brand 1 population, the brand 2 population, you have paired essentially the observation of tread wear. And so thus you have a dependent samples that you're taking. Okay. So let's talk about the setup in terms of the notation. Let's let y11 be the value that we observe in terms of our sample from population 1, and for, let's say, item 1 in that sample. Y21 is going to represent, sorry, I said that incorrectly. Let me restate that. Excuse me. Y11 represents item 1 in your sample from population number 1. Y21 corresponds to item 2 in your sample that came from population 1, down to, let's say, YN1, item N that was sampled from population number 1. Then let's let Y12 be, let's say, item 1 that comes from population 2, all the way down to Y sub N2, which would be item N that was sampled from population number 2. The key thing, though, is that Y11 and Y12 have something in common with respect to how this sample came about. Y21 and Y22 have something in common in terms of how the sample came about, and so on. So Y11, Y12 could be, let's say, Wheaties prices at Hy-Vee and Walmart. Y21, Y22 could be milk prices for a particular brand at Hy-Vee and Walmart as well, the same brand. So that's how our data, that's how we define our random variables. I could have done exactly the same definition with respect to the independent sample set of notes. In the end, it wasn't needed because of how we were going about investigating the statistics and the corresponding numerical quantities. Here, I do need to be that precise in my definitions. And the reason being is because of this. We're going to actually transform the form of our observed values to this form here. We're always going to take y sub I1 minus y sub I2 for the ith item in our samples that we're obtaining. And we're going to call that d sub I. So for example, with respect to the Walmart and Hy-Vee example, let's say that Walmart is population 1, Hy-Vee is population 2, and let's say Y11 is would be the Wheaties price, $4. Y12 is the price at Hy-Vee. And so that D1 is going to be 0.05 or 5 cents. And we're going to do that for every single set of observations that we have from our samples. So that now essentially you can say we have now one sample of differences. Now that we have one sample, we can essentially one sample, we can now basically go back in our set of course notes to what we did when we had one sample for one population mean and do all the inference procedures that we did then, now here. So, for example, we could find a sample mean and a sample variance, not for the y's, but now for the d's. Also, we're interested in the difference of two population means in order to make inferences to that. Now, since we're working with these differences, instead of writing it out like this, you could write it out now as, let's say, mu sub d. So the mean, population mean of the differences. And yes, we do have still two populations. But by using this notation here, that helps us differentiate it from what we were doing when we had independent samples. Now, overall, one can think of this particular subsection as relatively easy because all we're going to be doing is applying the inference methods, hypothesis testing, the confidence interval methods that we learned from working with just one mean. We're going to be now applying it to this particular section where we're looking at the mean of the differences. Now, why is working with dependent samples generally better to do than working with independent samples? Well, it comes down to this particular equation right here. One can show that the variance of the d bars, the sample mean of all the d's, is less than or equal to the variance of y bar 1 minus y bar 2 if this was treated as if we were having independent samples, like what we had with the last subsection. Well, why is this important? Well, for a lot of stuff that we do in statistics, we have an equation like this for a confidence interval, for example, where we have a statistic of interest. We add or subtract a value from a probability distribution, a quantile, and we take it times the square root of the variance of the statistic. And ideally, with these confidence intervals, we would like these confidence interval limits to be as close to each other as possible. In other words, we want a narrow interval, we want a short and length interval. And if that variance portion of that expression is smaller than if I were to use the variance from another calculation method, well, then that's great, because now I have a smaller range for my confidence interval. In terms of the lower limit, it's going to be closer to the upper limit. So from a practical standpoint, this is why working with dependent samples is ideal. Now, let's talk about, though, why this variance here is actually smaller. Let's think of it from an intuitive point of view first. Suppose I actually did an independent random sample from, let's say, Walmart, an independent random sample from Hy-Vee with respect to comparing the prices of the products at the two different stores. Well, there's a lot of different items at both these stores. It would be very unlikely that you would get exactly the same item from Walmart than you would from Hy-Vee if my sample sizes were, let's say, 10 a piece. And so because of that, because there's so many items there, there's going to be a lot of variability in these prices. Now compare that to the paired or dependent sample case, where if I had, let's say, Wheaties breakfast cereal from Hy-Vee and Wheaties breakfast cereal from Walmart, now there's going to be, those prices are going to be close together. They're going to be quite similar. They're not going to be probably exactly the same, but they're going to be quite similar. And so then when I subtract the two, then I have maybe a difference of like 5 cents. And so if I expand this to over a sample size 10, then overall what I'm expecting to see, since I'm always taking the paired samples, I'm going to see a smaller variance than if I would have took random samples separately from each of the stores. Now let's talk about this more in a mathematical context. Suppose we look at item 1 from one of the grocery stores, and we look at item 1 from the other grocery store where we do have a paired sample. And if I were to find the variance of this, then I can apply some of the methods that we've talked about in the past. This is going to be, let's say, 1 squared times the variance of y1, 1, plus 1, let me start over, plus negative 1 squared times the variance of y2, 1. Now, plus 2 times 1 times negative 1 times the covariance of y11, y21. So direct application of some stuff that we saw earlier in the course. So if I just simplify this again a little bit, okay. Now again, think of these Y's as being prices for the same product at the two different stores. Because these are the same product, we would expect a positive correlation or positive covariance between prices at one store versus another. Again, you would expect Wheaties to be very similar priced at Hy-Vee as you would Walmart. So because of this, this is going to be a positive value. So in other words, it's going to actually, since I have a minus there, it's going to lower my overall variance than if I were to have independent samples, because in independent samples, this covariance would be 0. So then we could rewrite our expression like this. Where for my dependent sample case, when I'm working with the variance of the difference, I'm going to have a smaller variance than if I was working with independent samples. And this inequality sign comes in the fact that this covariance is going to be positive since I'm working with the same items at the store. So that gives you some of the mathematical justification then for why, at least for a particular item, why the variance for the difference there will be smaller than if I were to treat everything independently. Now, what we actually have, though, is the variance of d bar. So, again, using methods that we've seen before, let me write this out in terms of the summation. I can bring that 1 over n squared out, or 1 over n out as 1 over n squared. Okay. Now, each of these items at a particular store are actually taken independently. So if I get Wheaties, that's going to have no effect on what I sample next. So because of that, and actually I should have a capital D there, excuse me. So because of that then, I can rewrite my expression like this. And we'll just go one more time. Just for completeness. So now I just have the variance. I have the variance of each of the corresponding differences, and I'm summing them up. Now let's look at this variance of D1. That's what this is right here. Notice how it's going to be less than if I were to have treated the samples as independent. So then the variance of D2, you're going to have the same similar thing happen. This variance of Dn, you're going to have exactly the same thing happen as well. And so because of that then, if you put this all together, that's why, in a mathematical context then, why the variance of d bar is going to be less than or equal to the variance of y bar 1 minus y bar 2. A very interesting result, a nice application of stuff that we've actually seen before. I sometimes will give questions on a test regarding this exact part here, so please be aware of that. Now, we've already answered this question then. Now, in a more general setting, outside of this class, you might take some more statistics courses, and you might run into something called a randomized complete block design. Well, what we're talking about here with these dependent samples where we have two population means, that's a special case of a randomized complete block design. In a randomized complete block design, you might be interested in the following hypotheses. where let's say you have T different populations, you're interested in, are the means all equal to one another, or is there one set of means unequal to one another? And the way that you take your sample is, again, you have this pairness, or you have this dependent sample that you're taking from each of the populations. So each of the samples are connected in some way. And this connection, you could say, is what's referred to as a block. So again, if you take another statistics course, you will often run into these kinds of in this kind of a setting. Typically in our kind of a course, or randomized complete block design is not discussed. That's why I'm not doing it here. But I do wanted to mention this connection to something that's a little bit more generalized that you may run into in another particular course. Well, what's a confidence interval now for this mu sub d, the population mean difference? It's exactly as what we had when we were dealing with one population mean before. The key difference is we replace the y's with the d's. So it's the same interval. So then, for a note here, please see previous discussions about its use then. For example, what happens to the need for the normal probability distribution when there's a large sample? Okay, so let's talk about an actual numerical example here. This example deals with some work that I've done with a pharmaceutical company in the past. And in particular, this pharmaceutical company was developing a new drug to treat schizophrenia patients. When I became involved with it, it was in what was called a phase 1 clinical trial. In case you don't know, there are typically 3 phases to clinical trials to determine if a new drug that's being developed is effective. Phase 1 is to determine, is the drug safe for people to consume? Can the body tolerate it? Phase 2 continues looking at that, but now it looks for a third item: is the drug effective? Meaning, it does it, let's say, cure someone of a disease or help them manage a disease. Then a phase 3 clinical trial then deals exactly with what phase 2 does, but now it uses much, much larger samples to make a definitive answer, to provide a definitive answer of, is the drug effective? Okay, so this was a phase 1 clinical trial. In fact, this was the second time that it was evaluated in a phase 1 clinical trial. So we were looking at how safe is it for people to consume. And it was evaluated at a number of different dosage levels. To make things simple for us, we're just going to consider the 3 milligram dosage level. And the drug was administered, and right before the drug was administered to people, at time 0, let's say, a test called the Continuous Performance Test, or CPT for short, was administered to a person. And then after that person was administered the drug, 4 hours after, this test, in case I didn't say this before, it's a psychometric test, was administered to the people as well. And this is what the test involved. The patient, or actually they would call them subjects in this case, a subject sits in front of a computer screen. And in front of the computer screen, you see a randomly generated number where the image is blurred a little bit. One number will appear every second for 480 seconds, and subjects will press a button whenever they see the number 0 appears. And what we were interested in measuring then with these subjects was what happens to the number of correct responses, meaning the number of times they pressed the button when a 0 appeared, which we called hits. What happens to the number of hits before the drug is administered and then 4 hours after the drug is administered? And the reason why this was of interest is that we were wondering, what are some of the side effects associated with this drug? Could it cause drowsiness? Could it cause blurred vision? Could it have some other detrimental effect then that would cause the person to change the number of hits that they would get? So you might, many pharmaceutical drugs have these kinds of effects where it might cause sleepiness. Well, if you're sleepy, you might not perform as well on this kind of a test. Now, alternatively, this drug possibly could be some kind of stimulant that I guess perhaps could help you be more alert and allow you to do better on the test. And so what we're going to do here is find a 99% confidence interval for mu d, which represents the difference between time 0 and time 4 on average, the number of hits in terms of generalizing to a larger population of people. So here's what the data looks like. This isn't the actual data. I'm not allowed to share that. So subject number 1, let's say at time 0 they got 47 right. And at time 4 they got 45 right. Do note that the number of zeros appears exactly the same for time 0 and time 4. So the difference then is 2. So they went down a little bit in terms of getting those zeros. Subject number 2, 34 times 0, time 4, 32. Again, a difference of 2. And there was a total of 10 different subjects in the sample. And so from that, we can find the sample mean, ends up being 2.8. So in fact, what you could do is simply add these up, divide by 10, and you get 2.8. You could also find the sample standard deviation. So what we could do is we take the d value, subtract off the mean of 2.8, we square it. So for person number 1 would be 0.64. Do that for every single individual, add it up, get 15.6. So then the standard deviation ends up being 1.32. Okay. So now we have some data. What's the first thing that you should do whenever you get the data? Plot it. Take a look at it. See if it makes sense, the data that you observe. Maybe come up with some initial ideas of what you think might happen when you do inferences to the population. So since I have such a small data set, I just simply entered it in directly into tin, create an object called time 0 for time 0 values, time 4 for the time number 4 values, or time 4 hour values. Put it all in a data frame to print it out nicely. And let's look at some box plots and dot plots. So here's what our data looks like. We got a lot of these 2 values. But what's very interesting to notice is this. Here's my line at 0. So the difference of hits, if the hits go down over time, this value would be positive because I take time 0 minus time 4. And notice that all the values are above 0. So at least in this sample for these 10 subjects, it appears that perhaps this drug did cause some kind of detrimental effect because the number of hits, the number of correct responses was going down. So now you should think about that then in terms of if I want to make inferences to the population mean of these differences, what do you think the conclusion will be? Well, again, we have a small sample size here, but this is starting to make me think, uh-oh, there might be a problem here with this drug in terms of it is causing some issues here. We can also look at a histogram as well. There's our histogram. Obviously, we have a lot of 2s there. And so a question for you. So the corresponding code is for those plots is in my R program. Make sure you understand how those plots were constructed. So some questions. So why didn't I look at separate box and dot plots for each time period? Well, here's what it looks like if I would have done that. And based upon what we learned for independent samples, when we look at this box plot, we would say, hey, there is a lot of overlap between time 0 and time 4 hits. That overlap might make me think, okay, there's really not much difference at all between the population mean differences. Well, what we're seeing here then is the problem with this extra variability that one would have with independent samples. This would be an incorrect thing to look at. When we do take into account how the sample was taken, and that this extra variability from person to person essentially is essentially the extra variability that would be there if you had different people is removed, so we have the same people, we can definitely see, hey, it looks like there could be something really going on here because this is all above zero. You wouldn't get that same conclusion if you would just looked at this particular plot. So what do you think about the normal probability distribution approximation? Remember, that would be essentially an assumption for working with the t-distribution in this case, and we do have a sample size less than 30. Well, obviously, we have some issues here with this normal probability distribution assumption. Again, as what we've seen in the past, or what I've described in the past, is that fortunately, these kinds of confidence intervals, the corresponding inferences, are what are often referred to as robust to non-normality. So even if we don't have a normal distribution, very often this kind of confidence interval still works out well. But even this situation, I might be a little bit hesitant and actually perform a different statistical method too to see if the results match up. And in fact, I did do that, and the conclusions did not change, where this other statistical method did not rely on a normal probability distribution assumption. So let's actually find the confidence interval. Let me jump over here to 10. So I'm going to find the differences, find the mean difference, find the standard deviation of the differences, state my alpha level, find my sample size, get my quantile for my t-distribution, and there we go. So again, d bar is 2.8. Now I just go to my regular code, or my code that we've seen before for a confidence interval for one population mean. D bar minus the quantile from the t-distribution times the standard deviation divided by the square root of the sample size. That's going to be my lower limit. Upper limit exactly the same, but I put a plus there instead. And then I put everything in a nice little data frame to print it off. Let me hop back over to Word again. Here is my confidence interval. I also show here in the notes of how you can plug in the corresponding numerical values into the appropriate part of the equation for the confidence interval. Please note on a test, I might ask you to do that just to verify that indeed you can actually do it outside of R if you really had to. I mean, it's fairly simple in the end. And so here's my confidence interval. I am 99% confident that the mean difference in the number of hits is between 1.45 and 4.15. Another way to phrase the interpretation is that in 99% of similarly constructed confidence intervals, meaning you go out, take a sample, get a confidence interval. Go out, take a sample, get another confidence interval, and so on. 99% of these similarly constructed confidence intervals will contain this population mean difference for the number of hits. So, some questions then. Is there sufficient evidence to indicate a difference in the mean number of hits? Yeah, there is. Notice I think the mean number of hits is between one difference is always positive. And again, since I'm taking time 0 minus time 4 to find these differences, that means time 4 is lower than time 0. Something's happening here. One's, let's say, maybe alertness, one's ability, excuse me, to make these judgments is decreased for some reason from taking this drug. What would you expect the plots to look like if there was not a difference, or if there was not enough evidence to indicate a difference between the mean hits? Well, I'll let you answer that on your own. Again, think back to when we were dealing with only one population mean, that section, what that kind of a plot would look like if there wasn't, if I was doing a hypothesis test of equals 0 versus not equal to 0 for the mean. Okay, here's a good reminder. Remember that the confidence level does not mean there's a 99% probability that this one interval contains mu sub d. Instead, it means that if many more samples were taken, we would expect on average about 99% of the confidence intervals to actually contain this mean. So here's a little bit easier way to perform these calculations in R. Use, as we've done before, the t.test function. So for the first argument, we have an argument called x. This is where you can put in essentially what you would refer to as population number 1. In this case would be times 0 values. Then y, that gives us our time 4 values, populate the sample from population number 2. My data is in a data frame called CPT, confidence level of 0.99, and here's a very critical part. There is an argument in t.test that we have not seen before called paired. In this case, we want to call it true, or we want to use the true value with it, because now we have dependent samples. And again, some people refer to these as paired samples, so that's where this terminology comes from. The default value for paired is false. And so when we use the same function for when we were dealing with independent samples, that's why I didn't include that. So if I go ahead and run this code, here we go. Here's our confidence interval that we've had before. Okay. Now, what if we use the same function now, t.test, but now we only work with the differences instead? So, maybe perhaps we can imagine that this indeed was just a one sample problem. So I say x equal d, use what we did in the previous section for one sample problems, confidence level of 0.99, and guess what? I get exactly the same thing. I purposely did this here just to emphasize the fact that we're doing exactly the same thing as for the one population set of notes, but now we work with the D's instead. Well, what about hypothesis testing? Again, everything follows from what we've done before. So let's take a look at the confidence interval method to do this hypothesis test. We state our hypotheses. Mu d is equal to 0 versus mu d does not equal 0. We're looking for, is there any kind of change in these hits on average? We state our confidence interval, and what this means in terms of our what this means is that we reject HO because 0 is not in the interval. What does this mean now in terms of the original problem? Well, there is sufficient evidence to indicate a difference between the average hits at the two different time periods. Well, what about a test statistic? Well, when we came up with the hypothesis test for one population mean, we looked at a very similar quantity in the middle of two quantiles from a t-distribution, but it was written in terms of the y's. Here, now I write in terms of the d's, so that now our test statistic then becomes d bar minus the hypothesized value of the difference of the means. And for us, it typically will always be 0. Very rarely would there ever be a case where you would want to look at something different from 0. Divide by the standard deviation, which is also divided by the square root of n. Okay, so how do we do then a p-value? Well, for a two-tailed test, take 2 times the probability of random variable t with n minus 1 degrees of freedom is greater than the absolute value of this test statistic. You can also do all this stuff in terms of one-tailed tests as well. I'll let you explore that on your own. There's, I think, a little bit later in the notes, we're going to look at it in a little bit, or in a little detail. But you should be able to do one-tailed tests based upon what we've done in the past. So, test statistic method now. State our hypotheses. State our test statistic is calculated to be 6.72. So again, here's d bar, here's S of d, and of course, here's the sample size. Something that's important to remember here when you have dependent samples. Note that the sample size is always going to be exactly the same for the two samples because since they're dependent in some way. I find my value, my critical value from a t-distribution. Again, I would use QT to do this. It's a plus or minus 3.25. Then I graph it out in step 4. So we can see that our test statistic of 6.73 is way out there. It's very extreme with respect to this t-distribution, meaning it would be very unusual to get the information that we did in our sample if the population mean was truly 0. So because of that, then, it must not be 0. So since 6.73 is greater than 3.25, we reject HO. Again, I expect to always see something like this on any kind of graded assignment, project, or test. So this means that there is sufficient evidence to indicate a difference between the average hits for the 2 different time periods. Thus, and this is key, the drug is having an effect on these patients. P-value method, well, I take that test statistic, I find the corresponding probability value, as you would expect, and this asterisk means times. This p-value is extremely small, meaning it's very unlikely to be that far out in the distribution if the null hypothesis was actually true. Well, let's take a look at then, what if we actually said these are actually independent samples instead? Would we reach the same conclusion? This is very, very important. So to do that, I use exactly the same code, but I changed, for emphasis, this paired to be equal to false. Here's my test statistic. Here's my p-value. Wow, look how large that p-value is. It's now 0.5 about. Before, we were getting something that was extremely small. Think about how this p-value then relates to these box and dot plots that we had. We saw a lot of overlap between the time 0 and time 4 values. This p-value makes sense relative to that plot. But what this shows you is there's this strong benefit of working with paired data, a paired sample, these dependent samples. Because if there truly is a difference between the 2 means, you're going to be able to find it much easier than if you were to treat it as independent samples. What about a one-tail test? In this case, most likely, because of how pharmaceutical drugs tend to affect people, a research hypothesis could be that I hypothesize that one will be less alert on average after they take the drug. So I would look for mu d greater than or equal to 0. So to do this kind of a hypothesis test, I can use the t.test function again with alternative equal greater. And as you might expect, we get essentially the same conclusion. Okay. You can also see here's the corresponding one-sided confidence interval. Again, think back why I'm finding a lower limit for this particular problem, rather than finding an upper limit. So that then concludes this section on working with dependent samples when you're doing inferences for the difference of 2 population means.